good search fails when each document is scored in isolation. You'll train a LightGBMRanker in Python that optimizes ranked results instead of plain classification accuracy. This is the setup you'll be able to run after this, which learns a group-aware ranker with a ranking metric and orders candidates for a query. I'm Professor Pi, teaching AI foundations with simple Python. Search and recommendation systems often need an ordered list, not just labels. Learning to rank trains models to sort items per query, so the most useful items appear first. People reach for LightGBM for this because it scales, handles features well, and includes ranking objectives ready out of the box. Success looks like higher relevance at the top of the list, measured by metrics that care about position rather than raw accuracy. At its heart, learning to rank asks a simple question. Given a query and several candidate documents, how do we score them so the best appear first? We teach the model with graded relevance per query, so it learns preferences inside each query group. The main strength is improving the top of the list where users focus. A weakness is needing query grouping and careful evaluation per query. We will build a tiny, readable example that demonstrates the gap between a pointwise classifier and a true ranker. Then improve ordering with LightGBM. You will see a toy dataset, a baseline classifier trained on a misleading feature, then a LambdaMART ranker that fixes ordering, plus validation and a simple rerank demonstration to show concrete top results. Now we create the toy dataset. This snippet creates a tiny, query-grouped toy dataset structured for a LightGBM learning to rank task. The matrix X holds 2 features per document, an intentionally misleading signal A and a relevance-aligned signal B. The vector Y contains graded relevance labels, which ranking losses like LambdaMART exploit better than binary labels. The array group encodes query boundaries, which LightGBM's LGBMRanker expects to form within query pairs. We also include DIDs as simple document identifiers and QID to mark query membership for later slicing. The print confirms the number of queries and documents you will rank. This quick setup ensures we can measure ranking quality rather than only classification accuracy. Next, we train a simple pointwise baseline to show the mismatch. This example trains a pointwise LightGBM classifier on a single misaligned feature and computes NDCG at 3. The variable YB converts graded labels into a binary target, which encourages separating relevant from non-relevant without caring about order among relevant items. We purposely feed only XA, the weak signal A, to LGBMClassifier.fit to mimic a common baseline that learns a probability of relevance. We then predict scores S and compute NDCG per query using NDCG score, averaging the results to get a single summary. Increasing N estimators may yield sharper probabilities, but it will not fix the objective mismatch. The printed NDCG shows how a reasonable classifier can still rank poorly. Now we switch to a proper ranking objective that learns ordering directly. This code fits a LightGBM LGBMRanker using the LambdaMART objective and evaluates groupwise NDCG at 3. The ranker learns directly from graded labels Y while respecting query groups via the group argument in fit, optimizing a loss aligned with ranking quality. After training, predict produces per document scores R that are only comparable within a query. We compute NDCG at 3 for each query and average the values to summarize ranking performance. Raising num leaves would increase model capacity, often improving fit, but potentially overfitting tiny datasets. The printed NDCG typically jumps well above the pointwise baseline, confirming that optimizing a ranking objective improves ordered results. Next, we add validation and early stopping, so training focuses on real ranking gains. This snippet adds group-aware validation and early stopping to the LightGBMRanker. We split by QID, so one query forms the training set and the other forms validation. Then derive group TR and group VA as the counts per query. The LGBMRanker.fit call passes eval set and eval group, so LightGBM can compute NDCG at 3 on the held out query each boosting round. The early stopping rounds parameter halts training when validation NDCG stops improving, and best score underscore captures the peak metric value. Decreasing early stopping rounds reacts faster but risks stopping too soon. Increasing it explores more rounds but may take longer. The printed best validation NDCG confirms the model learned useful ordering before overfitting. Finally, we show how to re-rank a single query and inspect the top results. This example re-ranks documents for a single query using the trained LightGBM LGBMRanker and lists the top results. We select the second query's rows with the Boolean masked IDX and obtain scores via ranker.predict, which are comparable only within that query. Using NumPy argsort in descending order, we compute an ordering and map positions back to document identifiers in DIDs. The first three form the visible search results a user would see. If you care more about very top positions, training with a smaller eval at like 1, 2 can further tune early precision. The printed IDs show the concrete, improved retrieval order that matters to users. In a real project, this toy maps directly to per-query logs and feature matrices. Replace the small arrays with your query IDs, feature store, and user signals. Use the same group-aware fit pattern. Evaluate per query with NDCG at the cutoff you care about, and re-rank the live candidate set with the trained model. Recap: learning to rank with LightGBM trains a model that optimizes ordering inside each query group. Use it when your metric values positions, like top results in search or recommendation. Caveat: it needs grouped data and careful per-query evaluation to avoid misleading averages. Next step: tune the model capacity by adjusting the number of leaves and learning rounds, while monitoring validation NDCG at your chosen cutoff. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.